in this experiment we will try to make a capacitor and measure the value of it. So, we will use two parallel plates to make a capacitor and measure its capacitance. Here you can see we have one copper plate and there is one more. So, there are two copper plates. So, using these two copper plates you can make a capacitor by placing say a polythene sheet, this is a dielectric material, keeping it one over the other. We have formed a capacitor now. So, our objective is to measure this capacitance using the X-Spice box. So, we keep the capacitor here and connect one lead to the ground terminal and another one to the terminal marked as in 1. This is the terminal that is capable of measuring capacitance. So, other lead of the capacitor is connected to in 1. So, after making these connections we move to the user interface and press say measure C on in 1. So, it says the capacitance is around 350 picofarads. So, we have measured the capacitance. Now, there is one problem with this measurement is suppose if you take, so you press this and make the measurement again, you will get a totally different value. See, it is quite high now. The reason is just by keeping this we are unable to control the distance between these two. So, a better way of making a capacitor is we use some metallic foil and paste them on both sides of this dielectric material. So, that way the capacitance is more well defined. So, we will use such a thing here. So, here you can see we have a small polythene sheet and on both sides we have pasted aluminum foils here. So, just paste aluminum foils and form a capacitor like this. Connect again one terminal to ground and another one to in 1. So, we have made the connections. Let us measure this. It is a 311.9 picofarads. Now, suppose say what will happen if this distance between the plates is increased. So, we will take another capacitance more or less the same area, but the thickness or the distance between the plates is much more. So, you can see 1.5 millimeter here and this is very thin. So, now we will measure this one, again make the connections and go to the screen, click on measure C on in 1, it is only 50 picofarads. You can see the area is more or less same, but the value is very less because the distance between them is too high. We have two capacitors here, both are 100 picofarads capacitors. So, we will measure them separately and also our objective is to measure the combinations, like if you connect them in series like this, what will be the effective capacitance, or if you connect them in parallel like this, what will be the effective capacitance. So, we will make both measurements. Before that, let us measure them separately, like connect this and so here you can see only one capacitor is there in the picture, we are measuring only one, other one is not in the circuit. So, the measurement says it is 102.2 picofarads. Now, let us change to the other one, remove this and bring the other one in the circuit, connect the other capacitor and that shows 100.3 picofarads. So, both are somewhere near 100 picofarads, they are never exactly 100. Now, we connect them in series like this, say both of them are connected in series, two capacitors, and make the measurement again. You see that it is around half of the value of a single capacitor. That means, if you connect two capacitors in series, their value is going down and the relation is given by 1 by C is equal to 1 by C 1 plus 1 by C 2. What will happen if you connect them in parallel, like this? We have connected them in parallel and make the measurement again. It says it has gone to 200. That means, if you connect more than 2 capacitors in parallel, the effective capacitor is the sum of the individual capacitance values. So, this is how you can study the effective capacitance of series and parallel combinations of the capacitors using XPICE. Let us explore the effect of AC and DC signals on a capacitor. See, for example, whether capacitor will be able to pass DC or will be able to pass AC or such things. Let us see how to do them. See, we already know that there is a programmable voltage source here marked as PVS, and we will connect a capacitor from PVS to say A1. A1 is another input. So, PVS, and we will make another connection to A1. A1 is one of our voltage measurement terminals. See, we make a connection like this, you can see here. First of all, let me just connect this directly. That means, the PVS is directly connected to A1, and we set PVS to say 1 volt, enter 1. So, PVS is set to 1 volt, and if you measure A1, you can see it is coming near 1 volt. Now, instead of directly connecting it, we are going to connect it through the capacitor. See, the connection is made through the capacitor, and if you measure A1 now, it is not getting that 1 volt, right. So, that means, the DC cannot pass through the capacitor, and we know that there is an insulating material between the two plates, that is why it is unable to get through. Now, let us see what will happen if you apply an AC signal, and AC signal is available on our terminal called sine here. So, let us connect a wire to sine, and we will connect the capacitor between the sine and A1. So, we will connect the capacitor in between this. So, let us take our this small capacitor which you already made. See, the capacitor is between sine and A1, and let us assign A1 to channel 1 and adjust the voltage and also adjust the horizontal scale. So, you can see that this AC is able to pass through this capacitor. Say, for example, if I remove this, the signal is gone. So, it shows that an AC signal can pass through the capacitor.